All right, let's jump right in. We're going to talk about a problem that is, literally everywhere, from your phone's GPS all the way to how the internet even works. And that question is, how do you find the absolute shortest path?
It sounds so simple, doesn't it? What's the quickest way to get from A to B? We ask this all the time, but when you get into computer science, finding the most efficient answer, well, that's a whole different ballgame. It's a really fascinating challenge, and the solutions are just brilliant. So to really wrap our heads around this, let's just think about a simple map. You've got cities, right? Those are our nodes or points, and then you have the roads that connect them. Those are the edges. Now, every road has a distance, which we call a weight. Our whole mission, the goal of this game, is to find the one route from our start to our destination that has the lowest total distance. Simple as that. Okay, so our first contender is probably the most famous one out there, Dijkstra's algorithm. And I want you to think of Dijkstra as the greedy sprinter. It's super fast, it's laser focused, and all it cares about is getting to that finish line as fast as humanly possible.
And its strategy is it's so simple, it's brilliant. See, Dijkstra's is greedy. What that means is, at every single step, it only asks one question. What is the absolute closest city I haven't visited yet? And boom, it goes there. No second guessing. It's the super optimistic approach that honestly works amazingly well, if the conditions are right.
So when do you actually use this thing? When do you unleash the sprinter? Well, it's perfect for any map where all the distances are positive. You can't have a road that's minus 10 miles long, right? That makes it perfect for stuff like your GPS or network routing. Anywhere that speed is the name of the game.
Now, the real magic behind how this works is a concept called relaxation. I know, it sounds kind of technical, but the idea is actually super simple. As the algorithm is hopping from city to city, if it suddenly finds a new shortcut, a path to a place that's shorter than the one it already knew about, it just updates its map. It's constantly learning and refining, pretty much saying, oh, wait a minute, scratch that, I just found a better way.
But what happens when the map gets a little weird? This is where things get really interesting. We're about to hit a fascinating plot twist, the negative edge.
So our greedy sprinter, Dijkstra, it's amazing at what it does. It's fast, it's efficient, but it has this one single fatal flaw. A flaw that can make its entire strategy just completely fall apart. So what in the world is a negative edge? Okay, think about it like this. Imagine a road that literally pays you to drive on it. You get a toll rebate, or maybe it's a power-up in a video game that adds time back to the clock. That's a negative weight. And Dijkstra's whole greedy logic of always go to the closest place, it completely breaks. What does closest even mean anymore when a path can actually subtract from your total distance?
So here's the bottom line. Dijkstra was built for a simple world, a world where all distances are positive. The second you introduce this idea of a road that pays you, its most basic assumption is just shattered. It's not the right tool for that job. You need something else.
And that is where our specialists come into play. Yeah, when the map gets tricky and throws these negative edges at you, you've got to call in the big guns, the algorithms that were built for exactly this kind of problem. So first up, we've got Bellman-Ford. Now, if Dijkstra was a sprinter, think of Bellman-Ford as more of a methodical detective. It doesn't make any quick assumptions. Instead, it patiently, carefully checks every single road on the map. And it does this over and over again, up to V-1 times, where V is just the number of cities. It's the super thorough, relentless checking that lets it handle those tricky negative edges without breaking a sweat. Bellman-Ford really has two superpowers. First, obviously, it can handle negative edges, no problem. But the second one, this is what's really cool. It can detect something called a negative cycle. What's that? It's like finding a loop of roads that pays you more and more money every single time you drive around it. It's basically an infinite money glitch. And Bellman-Ford can spot that, which, as you can imagine, is a huge deal in things like finance and arbitrage.
All right, our other specialist is Floyd-Warshall. Now, this one takes a totally different approach. It's like it flies up in a helicopter and gets this bird's eye view of the whole map. It asks a totally different question. What if we treat every single city as a potential middle stop or a layover between every other pair of cities? Then it just systematically goes through all of those possibilities to figure out the best route.
And this right here is its unique specialty. See, Floyd-Warshall isn't just looking for one path from A to B. Oh no, it's a total powerhouse. It calculates the shortest path between every possible pair of cities on the entire map all at once. In one go, it creates the complete ultimate travel guide for the whole network.
Okay, I know that was a lot to take in. So let's slow down and bring it all together. Think of this next part as your personal cheat sheet, a guide to help you pick the right algorithm for whatever problem you're facing.
All right, this chart right here, this is your ultimate cheat sheet. So the first question you should always ask is, are there negative edges? If the answer is no, Dijkstra's your guy. It's the fast go-to sprinter. If you do have negative edges, you need the robustness of Bellman-Ford. And if your goal is to find the shortest path between every single pair of cities, well then Floyd-Warshall is your answer, hands down. Now you'll see this speed row with some funny-looking O notation. Don't worry about that. All it is a simple way to measure how much slower an algorithm gets as the map gets bigger and bigger. And you can see Floyd-Warshall, well, it gets really slow on huge maps. And finally, let's talk about a few common mistakes to avoid. Some real pro tips here. The absolute #1 mistake is using Dijkstra when you even think there might be negative edges. It won't crash, it'll just silently give you the wrong answer, which is way worse. Also, really make sure you get that core relaxation idea we talked about. And for those of you who are going to code this up, pay attention to the little details, like how you set your starting infinity values. It's the small stuff that can trip you up.
So when you boil it all down, it's not really about finding the one single best algorithm, is it? It's about looking at the map of your problem and understanding its terrain. Each algorithm, each path, has its own strengths, its own weaknesses. So now that you have the map, which path are you going to choose?